So for this one, we're going to look specifically at, we talked yesterday about how the particle goes around in a circle, and I think that you guys kind of got the visual for that. But now if those, bless you, those questions we were looking at just, in part A and B, we're looking at it just like initially as it comes in, as it gets deflected or up. But if it kept going, like if it was a larger space and it could go around in its full circle, it would create even a radius, right? Okay. And so we're going to look now at circular motion with this. So your notes here, it says, as a charged particle travels through an external magnetic field, the magnetic force acting on the charged particle accelerates the particle. Not in terms of speed, but in terms of direction, which is a circular path. So from our centripetal acceleration lesson in Physics 20, you remember that even if the actual speed of the object isn't changing, it's still experiencing acceleration because it's always changing its direction. Because velocity is a vector quantity, if it's changing direction, it has acceleration. So what we can then assume for these questions, if we're given information about circular motion, what is causing this circular motion for these particles? The charged particle travels through an external magnetic field. The magnetic force acting on the charged particle accelerates it. So what force is causing centripetal motion? Magnetic force, okay? So we can make the assumption then that Fm, magnetic force, is equal to, because it's creating centripetal force, okay?
Always?
For our circular motion questions, yes. So, let's make a note. Just as Lisa's saying, can we use this rule? Yes. So use this for any problems dealing with radius of curvature, because if it starts to curve around, we can find its radius since we know it's going to go, if it had the opportunity, in a full circle. For charged particles in a magnetic field. So that's where we can make the assumption. If you have a charged particle in a magnetic field, that it is, and you're given information about that centripetal or circular motion. So now what we can do is we can expand our Fm, we can expand our Fc, and develop new equations from that. So say our Fm from yesterday's lesson, I'm just going to move it over a little bit here. Our Fm is Q times V times B perpendicular. And our Fc from Physics 20, we know, well, F is always our mass times acceleration. So we go mass times centripetal acceleration, or A subscript C. But say we're given information about radius, so we need to expand acceleration into a further formula that we did in Physics 20. Which one would that be? What does AC equal? Look at your formula sheet. Which one involves speed and radius? B squared over R. That's the one that we will use. So we have our Q times V times B perpendicular equals M times V squared over R. So now you can simplify this a little bit, because I have V on both sides. Here's V squared, and here's V, so I can cross those out. So a simplified version is Q times B perpendicular is let's solve for R.
There should still be a V. Yeah.
Oh, thanks, sorry. Yeah. Now let's rearrange to solve for R. So if we did that, we would have R is equal to M times V over Q, V perpendicular. So now let's just make some observations about how R would be related to everything else. So is R inversely proportional or proportional to M? Okay, and to Q and to V. So just when you're going through, if you might have to do some, if you were ever asked, you know, you were given a graph of R versus M or something, you can look and see, well, what type of relationship should it be based on a formula like that, okay? All right, so let's do a problem where we have to kind of use this. An alpha particle enters a 1.2 Tesla magnetic field, causing it to turn with a radius of 2.34 centimeters. Determine the speed of the alpha particle as it enters the magnetic field. So we are told our V perpendicular is 1.2 Tesla. Our R is 2.34 centimeters. I'm going to put that into meters, so divide by 100. And we are looking for V. And again, I like to put it as kind of a cursive small v, so I know I'm not looking for voltage. I'm looking for speed. Now, I'd encourage you to actually write out Fc equals Fm and develop your formula from there rather than just copying it, because then it gives you practice, because you'll have to make your own formula, say, on a test. So practice writing it out. Once you get the hang of it, you probably won't need to write it out every single time, but to start with, you should be practicing it. So I want to solve for V here. So now, when you're thinking about your V, this is the speed as it enters the magnetic field. So it's like the V final of it coming out of the accelerator. That'll make more sense after this next example too. So then V is equal to Q times V perpendicular times R divided by M. So my charge, it's an alpha particle, so that's 3.2 times 10 to the negative 19 coulombs times by 1.20 Tesla times by 0.0234 meters, all divided by 6.65 times 10 to the negative 27 kilograms. And that's a data booklet, from your data booklet. So plug that in your calculator. You get 1.3512 times 10 to the 6 meters per second to sig digs 1.35. And it's just speed, so we don't have to put a direction.